Well, cosmic time basically says that there is a preferred time coordinate in the universe, right? Such that at constant time slice, when that time is constant, the universe is homogeneous and isotropic, right? So that's the definition of cosmic time.
How do we like when we talk of like universe expansion? How do we actually find that?
This is the time coordinate t that you have introduced, right?
How do we give the numerical value?
That we'll see. I mean, you want to know the value of the cosmic time today, right? Yeah. So that we have not discussed that, right? Yeah. So we'll see how. I mean, right now all I have said is that based on this symmetry principle, right? We assume that there is some cosmic time, right? And in that cosmic time, using these various symmetries, you have written down the form of the metric. Right? That's all you have done. You have not said how to measure this cosmic time, right? Today. Is it clear? Okay, so let me write down the form of the metric. Okay, so this d omega square I'll use as a shorthand notation for d theta square plus sin square theta d phi square. Okay, this is just so that we don't have to write this long expression, we just write d omega square. Now, let's suppose T naught is today's time. So we don't know what it is, right? That we'll see later how we define it. But based on whatever you have said so far, we cannot even measure T naught uniquely because this form of the metric, right, is invariant under T goes to T plus constant. Right? All you have to do is change the definition of A of T. Right? So you have to fix something else to be able to say what it is today. Right? But the difference in time we can measure. Right? Okay. So T naught is the value of T today, and we define A naught as A of T naught. Okay. And lambda we'll define in another quantity lambda of T as A of T over A naught. Okay, so lambda is a ratio of the A of T to today's value of A of T. Okay, that's the definition of lambda. So using this definition, we can write ds square as minus dt square plus lambda of t square A naught square and now if we define rho definition, a new coordinate, rho is A naught times R. Then we can write the metric as minus dt square plus lambda of t square times d rho square on 1 minus k over A naught square rho square plus rho square omega square. Here I should have written that k is 0 or plus minus 1, right? That's what we had said. Is this clear? Now here one thing you notice from this form of the metric that if A naught is large, then K over A naught square is small. And if A naught is large enough, so that we cannot actually see the effect of this term, there is some term in the metric, right? To be able to see it, it has to be certain, has to have certain value, otherwise experiments may miss it. So if A naught is large enough, right, so that experiments cannot distinguish, we cannot see this term, then the metrics for k equal to 0 and plus minus 1 are all the same. Is that clear? Right? If this term you cannot see in an experiment, right, then you can see that the k dependence goes away. Right? This is the only term where k appeared in the metric. Yeah, exactly. So k is 0 or plus minus 1, right? A naught is something which is today's value of A, right? And all I am saying is that if A naught is large enough, then you will not be able to distinguish between k equal to 0 and k equal to plus minus 1. K is some function, right? Cosmology is described by this function, right? So we'll see later how to actually determine A. Okay, what experiment should you do? Right? But at this stage, all I'm saying is that if A naught is large enough, then after you make this change of coordinates, right, you just don't see the distinction between k equal to 0 and k equal to plus minus 1. Okay. So if your experiment shows that k is 0, right, suppose all your experiments are consistent with k equal to 0, right, we cannot really conclude from there that k is actually 0, right. All we can conclude is that a0 is sufficiently large so that we cannot distinguish k equal to 0 from k equal to plus or minus 1. Right? So experiments will never tell you that k is 0, right? It will only tell you that A naught is very large. Or it will tell you what the value of k is. Right? If A naught is not very large, then its experiments may be able to distinguish this. And then the sign of this, once you detect this term, right? Then the sign of that term will determine whether k equal to 1 or minus 1. Right? And then the magnitude will determine what A naught is. But if we cannot see this in the experiment, right? Suppose the experiment show that k is as if 0, then you cannot determine k or a0. Right? All you can say is that the a0 is very large. Is that point clear? Okay. So this is important because our current universe is like that. Okay. All experiments that we have done in the current universe shows that it's as if this term is 0. Okay. But that doesn't mean that k is 0, right? That only means that a0 is very large. If you increase sufficiently, unless k is 0, then you'll never know the sign, right? If k is non-zero, then indeed by increasing the accuracy of the experiment, you will be able to figure out this value, right? So once you figure out this value, right, then it determines both k and a0, because k is supposed to be plus or minus 1, right? If k is non-zero, it's supposed to be plus or minus 1. So the sign of this term will tell you whether k is equal to 1 or minus 1, and then the magnitude will tell you what a0 is. Yes.
Has some row dependent rules. For example, if you get some different divisions, then what about the effect of this?
Yeah, indeed. So you try to detect this by observing over very large distance, right? But you have a limit of how large a distance you can see, right? And what I'm saying is that from whatever you have seen so far, right, we have not detected the effect of this term. Exactly, right? So all the experiments that we have performed so far, right, is consistent with this being 0.
All these measurements are just the speed measurements of the galaxy.
No, there are various measurements which have come together for detecting this. Okay, so not just the speed measurement, there are various other measurements that one does to eventually make this conclusion.
The conclusion is this A naught is very large.
Exactly. So the conclusion is that current universe a0 is so large that we cannot detect this term, right? Which makes life simple in some way, because that says that all calculations that we need to do, right, we can just set k equal to 0, right? And if we set k equal to 0, then this metric is just a flat metric, right? You can use Cartesian coordinate and write dx squared plus dy squared plus dz squared, and that makes the calculation simpler. So I'll keep k for now, but this is something we should keep in mind. Okay, then in actual practical calculation, if you see that you are not being able to do some integrals, just set k equal to 0 and do it. Yeah, but if you can find any coordinate system, right, in which this is true. See, otherwise you will see this here. I mean, I have chosen this so that this factor is 1 today, right? It looks like a flat metric. Otherwise, it will show up here, right? It will, I mean, if we rescale it by coordinate, which is not like this, right, then that large number will go into lambda. Right? Lambda will not be 1 today. Okay, and that will have its own effect, right, which will be able to detect. Is that point clear? See, what will happen there is that it is true that you suppose you don't rescale by this, right? A0 is very large, A is very large, right? You keep it like this, but then this will also vary rapidly if A0 is actually large, right? So that effect you can see. So it's a combined effect of all this, right, that you have to use to determine these numbers, right? Because otherwise, by making a coordinates transformation, you can go from one to the other. And I wrote the coordinate this way because so that today, right, it looks approximately Minkowski in this coordinate system, right? So this coordinate system is coincident with the standard Minkowski metric. Well, I have not said anything so far, right? T is some time, right? But the fact that this looks like Minkowski, right, means that this T has something to do with the time that we see. But we'll make it more specific in a few minutes. Right? T is which observer's time. Is this point clear? Okay, so you can go back and forth, right? If you try to make this large, this will also become large. Okay, ultimate experiment measures something which is coordinate independent. Okay, now I talked about some geodesics last time. Let me now describe a specific class of geodesics. So let's take the point to consider a curve in space time corresponding to r theta phi fixed. That means not function of u, and t is a function of u. That's a curve. I am not claiming at this stage that this is geodesic. So is this clear what kind of curve this means? Right? This means that you are at a fixed position in this coordinate system, okay, and time is moving, evolving. You are at rest in this coordinate system, right? That's what this means. Right? The position is not changing as the path goes, only time is changing, right? So if you eliminate u and write these as functions of t, that means this will be constant. Right? They are not changing as a function of t. So I can always draw a curve in space time, right? Anything that I like, right? Let's take this curve. The claim is that this is a geodesic. Claim this is a geodesic. For t being any function. No, I am not saying t being any function of u. T is some function of u, right? Which you can determine, which I'll by solving the geodesic equation. Yeah, T is u is a parameter, right? So if u is, so it can be any function of u. It's a geodesic because I have not told you that u is affine parameter, right? You can always rescale. I mean, as long as r theta phi is not depending on u, right? Then T being any function of u is a geodesic, right? As long as you don't claim that it's affine, u is affine. Is this statement clear? Okay. Yeah. So what he said is that if I take T to be any function of u, right, that may not be a geodesic because you have to solve this equation, right? d2t du square plus gamma t mu nu dx mu du equal to 0, right? These are the geodesic equation. Right? Any function of t may not satisfy this equation, right? But this equation was derived assuming that u is affine parameter, right? If you don't demand that u is affine parameter, then you can always choose u to be anything that labels t, right? That will not satisfy this. Okay, so let's give the proof, right? Again, the proof is based on symmetry principle. So proof, if I can prove this for r equal to 0 origin, then we have proven it in general by the homogeneity, right? If a result is true for initial that r theta phi at the origin, then I have proven it, right? So take r theta phi to be 0. R theta phi to be 0 theta naught phi naught, right? Once r is 0, then theta naught phi naught theory doesn't matter. T is changing, right? Yeah, so that's why it's a carbon. Okay, so in this, if you draw T versus R, right, then it's a vertical carbon. So let's try to prove it for this. Okay. Now we know that starting from any point in space-time, we can get a geodesic if we specify the first derivatives. Because geodesic equation is second derivative, right? Now let's take u to be affine. Okay, geodesic equation is second derivative. So if we give the initial point and the first derivative, we have a that corresponds to an affine point. Sorry, that corresponds to a geodesic. That can give a geodesic, right? By solving the second order equations. Okay. So let's take the initial condition. To be r theta phi t to be 0, theta naught phi naught. So 0, let me now take this to be 0, 0. The rest to be completely and some t naught, say. Okay, theta and phi, I mean, it doesn't really matter at the origin what theta and phi I choose. I just chose theta and phi to be 0, 0, right? Because at the origin, theta phi coordinate is irrelevant. And now I also impose that ddu of r theta phi t is 0, 0, 0 and something v naught. Yeah, so here I have taken to be theta naught phi naught, but at the origin it really doesn't make a difference whether you take theta naught phi naught to be whatever value of theta naught phi naught you take, right? So I'm just taking this to be 0, 0. Okay, at the origin it describes the same point. All values of theta naught phi naught describe the same point, right? Because it's the origin of the polar coordinate system, the r theta phi. Okay, so ddu of this I take to be 0, 0, 0 and v naught. Okay, this is important here. So which means that theta naught, phi naught are not changing. Okay, so the speed that we have taken, okay, is only along the t direction. Okay, given this condition, right, we want to know what this geodesic will be. Okay, now what do you think the geodesic will be? Will this be non-zero? No, well, this is for general case. I'm not. Let's not use the fact that A naught is large, right? It's not. It is not going to be necessary. Yeah, the maximal is so it's a maximally symmetric space time, right? Imagine that we assume that r theta phi becomes non-zero at some point, right? Using this. Here at the origin. If it becomes non-zero, then you prefer direction, it becomes non-zero, right? But it's maximally symmetric. So unless the initial condition makes that non-zero, right? You cannot choose an arbitrary spatial direction and say that the particle will move in that direction. So just from this argument, rotational symmetry, right, we know that r theta phi will remain 0. Is this point clear? That if you start at the origin at 0 speed, right, then what this is saying is that this is not flat space time, right? Because lambda is changing. Okay? Nevertheless, by just the fact that this is rotational symmetry tells us that if you start at 0 speed at the origin, then it simply cannot move in change its position, because in order to change its position, you have to pick a preferred direction. Right? And there is no preferred direction because of the rotational isometry. Okay, so rotational isometry implies that r theta naught, r theta phi remains 0 at all time, at all u. Okay, so only t changes, because there is no isometry that prevents t from changing. Is this argument clear? Once you have proven it for r equal to 0, then by homogeneity, it is true for all r. Right? Any point that you pick, right? You can always choose your coordinate system where that point is origin. Right? That's because homogeneity tells us that you can make change of coordinates without changing the form of the metric, where that point is the origin, right? And then you can apply this argument. Yes.
With r remaining 0.
Yes.
Theta phi is still changing. That would also be consistent with.
But that change is irrelevant, right? Because theta phi changing, right, doesn't mean that the point is moving. Right? So you might as well take theta and phi to be 0, 0. Right? So physical conclusion is that that point in this three-dimensional space, right, remains fixed. Right? As the along the geodesic, right, only time changes, that point remains fixed. Is this argument clear? Right? Just by rotational isometry, that if you keep think of a space time, right, which is time varying, right, because A depends on time. Okay, so it's not flat Minkowski space. Okay. Nevertheless, as long as you have rotational isometry, and if you start from a point at rest, it must remain at rest, right? Because by symmetry, it cannot move in any direction. Right? That's essentially this argument. Okay. So points which are fixed in this coordinate system, for which r theta phi is fixed. Okay, curves for which r theta phi are fixed, but t is changing. Those are all geodesics. Is that clear? So these are called co-moving geodesics. This r theta phi t coordinate system is what is called co-moving coordinates. Okay. And the geodesics in which r theta and phi remain fixed are called co-moving geodesics. Okay, these are not the only geodesics that we have in this space time, but these are special kind of geodesics. okay, which are important as I explained in a few minutes. Yes. Oh, because we know that given an initial condition, right, you can always find the geodesic, right? It's the second order differential equation, these are the initial conditions, right? So that geodesic, the US determine T as a function of U by solving the equation, right? And whatever it is, that is a geodesic. Okay, this argument only says that with this initial condition, R theta phi doesn't change. Now let me explain why these are important geodesics. That all objects in the universe or so most objects in the universe are approximately co-moving. That means they move along co-moving geodesics. Or you can say on the average, they are co-moving. These are called co-moving geodesics, right? The geodesics for which R theta phi remain fixed and only T changes. Okay? That's the name. This is what we call co-moving geodesics. Exactly. Yeah. In this coordinate system, that means that it's sitting at a particular point. But in general relativity, right, that notion is a little strange, right? Because when you say sitting at a particular point, you need a coordinate system, right? It's in this coordinate system that it's sitting at a particular point, and then just a time is evolving. Right? Those are the co-moving objects. Objects which are stationary in the R theta phi coordinate system. Yeah, you can. I mean, this is a metric. That is a global metric, right? The metric that I wrote down, right? Okay, you can say R theta phi may not be valid coordinate system everywhere, right? Because this 1 over R square minus 1, for example, right, means that R equal to 1, this coordinate system breaks down. You just change coordinates, but that coordinate will remain fixed. Right, on the sphere, this problem comes because on the sphere you cannot have a global coordinate system, right? So you have to change coordinates. So, but that coordinate will remain fixed. Yes. Imagine that we take an object today here, right, and give it a push. It will move, right? And for them, R theta phi will change. I'll explain why, right? Approximately co-moving. Approximately means what? Okay. Approximately means that their speed with respect to co-moving objects is small. Small compared to the speed of light, right? Because we have set speed of light equal to 1. Okay. So it is true that not every object is co-moving. Most objects are not exactly co-moving. Okay. But first, let's understand that on the average, the objects must be co-moving. Right? Why is that the case? Okay. Imagine that on the average, the objects are not co-moving. Right? All the objects are on the average moving in some direction in space. Then the corresponding energy momentum tensor that the object produces will not have the rotational symmetry. Right? The rotational symmetry means all directions are equivalent in this coordinate system, right? Imagine that all the objects on the average are moving in one direction. Right? then the rotational symmetry will be violated, right? The energy momentum tensor is not going to respect rotational symmetry. And after all, the energy momentum tensor is the source of gravity, right? So the metric is rotational invariant. It better be that the energy momentum tensor is rotational invariant. Yes, but you have already chosen a specific coordinate system, right?
Moving coordinate system in which everything velocity of the all the object.
But that will not produce the metric that you have written. This is a metric that you have taken, which is the rotational invariant metric, has already been said that has that form in this coordinate system, right? So r theta phi, right, t, that coordinate system that you have chosen, has that gone in this in the definition of the metric, right?
Similarly, still get the same.
No, in the moving metric, what will happen is you will get a g t phi component, a tr component, right? Imagine that you have this at lambda t squared dt square and then lambda t squared times dr square, right? All that. So dx square plus dy square by dz square. Normally, when you take a moving coordinate, Minkowski metric remains unchanged. But this is not Minkowski metric, right? So what will happen, you will find is in a moving coordinate, if you make a coordinate transformation, you will get a g tr, g theta, t theta, these kinds of components, right? Which we have taken to be 0, right? We have already said that we have made a coordinate transformation to set those components to 0, right? So from that perspective, we have already chosen a very specific coordinate frame, right? And now you cannot go back to moving coordinate system. Well, you can if you want, but then the form of the metric has to be changed, right? As long as you demand that the coordinate system that you have chosen is such that the metric has this form, right? Then on the average, right, you cannot have objects moving in one direction, because that will break the isometry that you have used. Is that clear?
Same definition of co-moving coordinate when we give, say initially at some r theta phi coordinate, but after the universe expanded, the points will be somewhere else, and we are again assigning the same r theta phi coordinates to this. Like this r theta phi is taking care of the expansion.
Yes, it will. I mean, so far you have not even said that the universe expands, right? It could contract also, or it could remain stationary, right? Lambda of t could be just constant. But indeed, yeah. So this is saying that r theta phi is a specific coordinate system, right? And the stretching of the universe, right? The stretches, the points. So this says, okay, if all objects in the universe are co-moving, right? That means that r theta phi coordinate is fixed. Then it's clear that the distance between them, right, will get scaled by lambda t. So look at the form of the metric, right? Lambda t square multiplies the dr square, let's say flat space, dx square plus dy square plus dz square term, right? If the points are fixed in the xyz coordinate system, then the physical distance is gets multiplied by lambda t, right? So if lambda t changes, that physical distance will change. Okay? But before we do that, right, you have to first understand that the physical objects, that the objects that we see in the universe, right? What kind of objects are they, right? If they themselves start moving, right, then maybe universe is expanding, but those objects are coming together, right? Remaining keeping the distance fixed. Because you have to first make sure that that is not happening, right? That the objects that we see are actual co-moving, are approximately co-moving, right? So for that, the first observation is that on the average they must be co-moving, because on the average they move in one direction. That will destroy isotropy, right? Because the energy momentum tensor will not be isotropic, right? It will prefer direction. If on the average they are co-moving, right, then in order for them to be far from being co-moving, right, their speed with respect to the average has to be large, of the order of the speed of light. Right? And most objects that we see in the universe are traveling at speeds that are much less than the speed of light. Right? They are not moving at speed of light relative to each other. Right? So if the average is co-moving, right, and if the speed of each object, right, is small compared to the speed of light, then they must be or nearly co-moving. Is this point clear? It's just that in the solar system, right? We are moving with respect to the sun, but that speed is much smaller than speed of light, right? In the galaxy, different stars are moving relative to each other, right? But that speed is also much smaller than the speed of light. It's just an experimental observation, right? So if the average is average speed is 0, right? That's a co-moving object, right? In a co-moving frame, on the average, there should be no motion. Right? Otherwise, the isotropy will be destroyed. Right? And if the relative speeds are small, right, compared to the speed of light, then it better be that each object is moving in the co-moving frame but with small speed. The lambda appears.
Lambda of t takes over and has a time evolution of
Yeah, so the homogeneity isotropic is an indirect argument. Homogeneity and isotropic told us that on the average, objects must be co-moving. Right? Then the experimental observation that the relative speeds of objects are small compared to the speed of light tells us that each object is nearly co-moving. Right? And if each object is nearly co-moving, then the expansion of lambda is basically changing the relative distance, physical distance.
making the dynamics themselves homogeneous.
Well, see, so far we have not discussed dynamics, right? This argument is indirect. Okay, we are using implicitly dynamics that in order for the metric to be homogeneous and isotropic, the energy momentum tensor better be homogeneous and isotropic, right? So it couldn't be that all the objects are moving in one direction. Exactly. That's right. Exactly. Yeah. Exactly. Yeah.
Here also we just started with saying that this r theta phi is not changing and it's not a function of by saying that. But in general, when we consider any particle moving, that can be depend on what sort of.
Yes, but as long as the particle motion is the speeds are small compared to c.
Derivatives are very, very.
Exactly. Right. So I'm not saying that these are exactly 0. Right? But because speed of light is the measure of is the unit of speed that you have chosen, right? We'll say that the motion is small as long as it's small compared to speed of light. Okay. And here I should also add, although this doesn't follow from the logic that I have described so far, okay, that I said that the microwave background is homogeneous and isotropic. Okay. It's homogeneous and isotropic in the co-moving frame. If, for example, we take a co-moving frame, okay, if you take a homogeneous and isotropic microwave background and take a spaceship and move in one direction at high speed, it will not remain isotropic, right? Because of the Doppler effect, yeah, the temperature in the forward direction will become larger, right? Because you will see higher frequency, and temperature in the backward direction will become smaller. So microwave background also is homogeneous and isotropic in the co-moving frame. Right? Now, why this is the case? The logic that I have given so far doesn't explain, because the energy density in the microwave background is so small, right, that doesn't really contribute to the metric today. But it's a relic of the early universe. Okay, in the early universe, we'll see that the microwave background was the dominant form of the energy, and there, in order for the universe to be homogeneous and isotropic, right, it better be that in the co-moving coordinates, the microwave background is homogeneous and isotropic. Indeed, yes, I agree. Yeah, right. So, that's not the way it was originally introduced, right? But indeed, when we said that, okay, we take this choice to be the one in which the microwave background is homogeneous and isotropic, right? But that can now to be translated back by saying that it's the fixed r theta phi coordinates that is homogeneous and isotropic microwave background. Right? I mean, whether the microwave background is homogeneous or isotropic, right, is not a coordinate dependent choice. Okay, it's a coordinate dependent choice, but the fact that the universe is homogeneous and isotropic is not coordinate independent, right? That's a statement of isometry. But the microwave background becomes looks homogeneous and isotropic only in specific coordinate system, and those are the co-moving coordinates. So this point we are going to make use of, right? That if we are now talking about different objects in the universe, okay, we'll take those different objects to be co-moving. Okay? And then you have to correct for small errors because each object is actually moving with respect to a co-moving object. Okay, in the r theta phi t coordinate system, each object is not exactly stationary. Right? They may have small motion, and you have to correct for that in any experiment. But if you average over many objects, right, then you expect that those corrections will average out. Exactly.
And then we will see at the center there is a band. We will say like this is the radiation from the galaxy at a different temperature.
Yeah.
We will remove that also.
Yeah.
Then we will get this homogeneous and anisotropic background.
Yes.
Yeah. So these co-moving coordinates come from the fact that we remove this dipole.
Exactly. Right. So the fact that you have to remove this dipole anisotropy, right, is a statement that you are not exactly co-moving. Right. We go to the co-moving frame by removing this dipole anisotropy. Right. So what he is saying is that the way to determine, right, what our speed is related to co-moving object, right, is just look at the microwave background and look at the anisotropy. Right. If we move with respect to microwave background in some particular direction, we'll see an asymmetry. Right. It's dipole asymmetry because the forward and backward directions will show different temperature. So knowing that asymmetry, right, we can figure out what exactly is our speed related to the microwave background. Right. So even if we are not co-moving, right, you can correct for our not being co-moving by making that correction, by correcting for that speed. Yes, it does. Right, which is counterintuitive because of GR, right? GR does say that there is no absolute frame, right? But nevertheless, just like in Schwarzschild metric, right, there is a preferred frame in which the metric was symmetric, looked symmetric. Right? So here also there is a preferred frame in which the metric is symmetric. Metric looks manifestly homogeneous and isotropic, and that's the co-moving frame. Right? And the statement is that in that frame, the objects must be at rest on the average, and the microwave background should be isotropic on the average. Well, this we cannot explain right now. If the microwave background energy momentum tensor was a major part of the of what is responsible for the producing this metric, then the same argument will tell us that microwave background should be homogeneous and isotropic in the co-moving coordinates, right? Because imagine the microwave background was not isotropic, right? There is a preferred direction in which the temperature grows, right? Then that would mean that that kind of energy momentum tensor will not be able to produce the homogeneous and isotropic metric that we have, right? So if microwave background was a major component of the energy momentum tensor, then it would be this argument would work, right? Right now this argument doesn't work, but what we will see is in the early universe, the microwave background did form a major component of the energy momentum tensor, and that's why it's today looks homogeneous and isotropic. We have basically evolved from the early universe. Exactly. Exactly. But things, of course, you know very well, right? How we are going around the sun, right? The overall speed is harder to maintain, right? Because special relativity tells us that the inertial, all inertial frames are the same, right? So to determine the overall speed, our overall speed with respect to the home moving frame, right? We have to do more work. That we have to see what is the average home moving frame, and we have to find our speed relative to that. Or the center of the galaxy cluster with respect to the CMB frame. Everything is moving, right? Even as a galaxy cluster, things are moving. Okay, so all those speeds have to be added up.
So my question was, there only a dipole contribution. There's no dipole.
I think the way they subtract it, the dipole contribution by definition is the one which will have, which you'll see because of a motion in a particular direction. No, no, I agree. If you are moving in a circle, right, you will get other contributions also, right? Yeah, but those contributions, what I'm saying, those accelerations are known from other sources, right? See, accelerations are easy to detect.
Yeah, so I'm asking, so at the end of the day, even if you average over the galaxy, that will have a constant velocity, not a.
Exactly. Yeah, yeah. As long as you do the averaging over a large enough region, that will have a constant velocity and not an acceleration.
That's what we see from the dipole.
Exactly. That is dominant asymmetry.
When you say, you mean basically your. That's what you.
No, no. We are saying that in our today we are sitting here, right? Our r theta phi is not changing as a function of time. That's what I mean by saying it's in a comoving frame. So there is a coordinate system, right? But also the question is how our geodesics are.
I am
Yes.
and I want to get the
Well, the metric is independent. I mean, okay. I don't know what you mean by if you are a co-moving object and you can always change your coordinate system, right? Irrespective of what your geodesic is, right? So when I say co-moving object, that means in this coordinate system, r theta phi is fixed, right? Our trajectory in the space. So this co-moving object is a statement of what the trajectory of this object is in space time. Right? It's one of the geodesics, right? But which geodesic? These co-moving objects are special kinds of geodesics, which in this coordinate system correspond to fixed value of r theta phi.
So I can go it this object, this geodesic object.
Yes.
What will the metric look like?
In local inertial frame, metric always looks like eta mean. Yes, and first derivatives.
I'm saying like globally what will it? Will it look like the same?
I mean, you can find the local inertial frame and see how the metric looks like, right?
I just want to ask if it won't be necessarily look like the
No, TR theta phi is not the local inertial frame because lambda t, unless lambda t is constant, right? TR theta phi is not the local inertial frame of the object, right? Because to get to the local inertial frame, we have to make sure the first derivative of the metric is always also zero. Yes.
R theta phi, R theta phi to 0.
Yes.
This describes a particular object.
It describes a geodesic. R theta phi equal to 0 and t changing.
Yeah.
That's a geodesic. So what we argued here is that describes a geodesic, right? And then by homogeneity, r theta phi equal to constant and t changing is also a geodesic.
And saying that every object is approximately
Means that every object's geodesic, right, is very close to one of these. fixed r theta phi and t changing.
So every object is in space is fixed. Every object is close to 0, 0.
No, no, no. Any r theta phi fixed
Okay.
is a geodesic, right? So every object is described by r theta phi fixed t changing, right? When you say approximately, right, that basically means that r theta phi is not exactly fixed; they change a little bit, but that speed, right, the dr dt etc. are small compared to the speed of light, right? But you can certainly consider geodesics which are not of this kind, right? Those will not be called comoving geodesics. No, no, my metric I have already given, right? I am now quantifying the time evolution of the object in this metric, right? What trajectory you are going to follow in space time, right? What trajectory another star, say light years away, will follow in space time, right? Those are the kinds of things you are studying.
We are also approximately going to measure by comparison.
Yes, exactly. Yes. Distance will be like, I mean, it's clear, right? The metric, if you look at the metric, you can see what will happen to the distance. Yeah, plus r square d omega square, right? Let me put the n r square. So the metric will increase, the distance will change, right? Depending on what lambda is. In co-moving frame, they just remain fixed, right? But because of this scaling, right? If lambda t changes, then the distance will change.
Exactly like
Yeah, you can think of it that way. Yeah.
the distance is growing, like whether it's expanding or contracting by the period of the lambda function.
Exactly.
That we don't know.
That we don't know yet. Right? I'll now try to say how we determine that. Pardon? K basically is like 0, as I said, right? K, I mean, from whatever experiment you have done so far, right? Right? We cannot distinguish between K equal to 0 and plus minus 1 because A0 is very large.
You can't tell it the spatial part is R3.
No, not at this stage. Right? Because it's the fact that if it's a sphere, right? A very large sphere looks like a flat space. Right? Very large hyperbolic space also looks like a flat space locally. Right? That's the situation today. It's so large that we cannot distinguish between sphere, hyperbolic space, and flat space.
The idea of co-moving geodesics is just to say that you adapt coordinates. I mean, you don't have to adapt. You just should not move in the killing direction. That's the idea.
You don't move in the killing direction. Yeah, you can say that. Right?
If you're in short shift, if you're not moving in theta phi direction, those are the killing directions. So that's a co-moving. I mean, T is also a killing, but then
yeah, they are moving in T direction.
yeah, okay. Say simpler example is if you're on a sphere, if you're on S2.
Yeah, when you are preserving some isometries, right? Let me put it this way, right? You may not preserve all the isometries, right? But there is geodesics which preserve some isometries, right? In this case, rotational isometry.
Whatever stabilizes the
Exactly. But I mean, it is certainly not all the geodesics, right? Because I could have started with the initial condition where this is not 0.
I mean, that's yeah.
And then it will move in this frame.
That's like saying in R3 there are geodesics in which theta is like.
Exactly.
There's also the radial.
Exactly. Exactly. Yeah. Well, that K is not the same as this K, yeah, but indeed, on the surface, you will see the curvature. No, we'll see the effect of K. Right? If the space was smaller, right? We will see the effect of K. The spatial curvature is very small. That's what it said.
We also be curved as well. The observer itself.
Yeah, I mean the physics will be very different, right? I mean if K was, I mean if A0 was 1 meter, for example, right? Clearly, I mean that the physics will be very different. Right? In 1 meter, you will see, I mean the universe has ended, right? Yes.
I have heard the statement that galaxies which are very far from us are moving at speeds which are comparable to
But those motions are because of the increase of lambda t.
how is that statement? I mean, not
They are fixed in the r theta phi coordinate system, right? So that motion that you are talking about,
that is
right, is because lambda t is changing. That way, I think it will become clear when we describe how lambda t is determined, right? It will become clear how things happen. Okay, so now let's consider the following situation. Okay, let's suppose that this is us, and there is a star somewhere far away. Okay, and we will assume that both us and star are co-moving. Okay, if there are small speeds, we can correct for it. Right, we know how to correct for our speed. For the star, right, we don't know what velocity, what speed it has. But if we average over many things in that neighborhood, we can figure out. We can say that maybe average speed is 0. Right, so on the average, the star is also co-moving. Now, our position we will always take r equal to 0 because that makes life simple, right? The symmetry is manifest. If we choose our position to be r equal to 0, the star's position, of course, we cannot choose r equal to 0, right? Because star is not near us necessarily. Okay. But we can choose the axis along which the star is situated, right? And we take let's take this to be the z axis, theta equal to 0. Okay. So this is at some r naught, theta naught equal to 0, and phi, right? Phi actually can be taken anything. At the north pole, the phi doesn't really matter. Okay, but let's just choose phi equal to 0. Okay. So T naught is time today. Here we take theta equal to 0, phi equal to 0, and T equal to T naught. That is today. Now we are observing some light coming from the star. Right? Observing the star means you are observing some light coming from the star. That light is not emitted today, right? In the cosmic time, that would have emitted at some t equal to t1, say, some early time. So here I put t equal to t1. Okay, what t1 is will depend on how far the star is. Right? If the star is very far away, then t1 would have been very small because it would have been much earlier. Light would have to start much earlier. But whatever it is, at some point the light started at t equal to t1 and it's reaching us. To study this physics, right, you have to first determine which path will it follow. It will go along null geodesy, right? Light goes along null geodesy. But there are many null geodesics, right? So which path will it follow? Okay, in the r theta phi space. Any guess? What can we say? Co-moving, well, this light is not co-moving, clearly, because the initial speed of light is 1 compared to the co-moving object, right? Light is never co-moving, right? On the microwave is co-moving on the average, right? Microwave background corresponds to radiation coming from all directions, right? So light is never co-moving, right? But you have to somehow use the symmetry to determine what path will it follow. What can you say? Radial along z-axis. So if you take this to be z-axis on the z-axis to begin with, right? It will follow the radial direction along z-axis because the symmetry will tell us that if it deviates from the radial direction, right, then it has to deviate in one particular direction, breaking the symmetry, right? So you have lost the full isotropy, right? But rotation about this axis we still have. right? If it's situated on the z-axis, then the xy plane rotation, right, we still have. So if you move in the x or y direction, right, that breaks the isometry. So the light will follow. So light will follow some path. T r of t, theta equal to theta naught, phi equal to phi naught, or phi equal to 0. Sorry, theta equal to 0, phi equal to 0. And once you have understood this, then we can also see that if we had taken this to be theta naught phi naught, right, it would have been theta naught phi naught here. Sorry, this is 0, 0. If we had taken this to be theta naught phi naught, right, at some particular angle, it will still follow the radial geodesic. The theta naught or phi naught will not change as light moves around the geodesic, right? Because by symmetry, any radial direction can be brought into the z-axis. Is it clear? So the upshot is that along the geodesic, only r and t are going to change, right? Theta and phi are going to remain constant, and that's what you are going to use. So along the geodesic, theta, phi are constants. So the null geodesic will take the form minus dt square plus dr square or 1 minus kr square equal to 0 times a of t square. Let me write this as a0 square times lambda of t square. Okay. So we can write this as dt over lambda of t as plus or minus a0 dr over square root of 1 minus kr square. And then we integrate this from t1 to t0, and here from r0 to 0. Is it clear what I'm doing? I wrote dt over lambda t, right? Because t dependence I took on one side, and on this side you have dr over 1 minus kr square. A0 I could have put on the other side, but I have chosen to put on the right hand side. Now plus or minus, right? We can determine what the sign is. Right? You see on the left hand side, T0 is larger than T1. Right? The light started earlier and then you are reaching here. On the right hand side, right, this integral is negative because R0 is certainly larger than 0. Right? It is negative, so I should put a minus sign. Okay, so I can also write this as a0 times integral 0 to R0 dr over 1 minus kr square. Okay. This is what we call co-moving distance. Okay, so let me explain the physical interpretation of what this d is. So this is the distance, okay, along the spatial slice, right, at t equal to 0 slice. This would have been the distance on the t equal to 0 slice. Multiplying by the a0, right, basically means that we are measuring the distance in today's metric. See, t equal to t0 is today, right? In today's metric, the metric on the spatial slice, is a naught squared times this. Lambda is 1 today, right? By definition. So in today's metric, today the metric on the spatial size is a naught squared times this. So this quantity is the distance measured in today's metric, right? The light started from the star long ago, but the star is somewhere today, right? And this distance is measured along the spatial slice today between us and that star. Okay, so this is distance measured in today's metric.
Coming from time which is d1.
Yes.
The information that we will see, like let's say if we measure distance, then we will see the distance which the star and we had a long time ago. So it should be that much.
Yeah. So the point is that this distance measurement is the main bottleneck in doing cosmological experiments, right? You see, to measure the distance, you cannot use the same experiment to get both, right? One experiment will tell you what it will tell you, we'll see, right? That experiment by definition will not tell you about the distance, right? You need an independent measurement of the distance, right? And as you said, the distance, the light that is coming, right, is coming from the star earlier, right? So you have to correct for that. That star has evolved. Okay? So the distance is typically measured by what is called the standard candle, okay? Where standard candles are objects in the sky, right, whose luminosity you know from some other information, right? Maybe one of the standard candles is the type 1 supernova. Okay? The supernova, at least people believe that their intrinsic luminosity is known. Right? So now, if you observe a supernova, right, then we can see what the apparent luminosity is, how bright it looks, right? And depending from that, we know how far it has traveled, right? Because intrinsic luminosity is known. So use that information to reconstruct what the distance is today, right? Even though the actual light is coming from far in the past, right? So you have to correct for that. Okay, after correcting for that, we infer what the distance of us to the supernova is today, right? And that radiation is what you measure. Right? Yes. So that, yeah, it's not that you directly measure this distance. You have to do some calculation. But even before you do the calculation, you have to first identify objects, right, whose intrinsic luminosity you know, so that you can use that information to compare that with the apparent luminosity, right, how bright it looks in the sky, to get an information about the distance. Yes. So all of that has to be taken into account, right? So it's not one step process, right? You have two information, right, and you have to solve for use both those informations to solve for the distance. Yes. No, distance is very clear. What I have said, that star is in a fixed co-moving object, right? So it is this. This is the distance. That star is somewhere there today, right? In time slice. Exactly. So this is direct distance in the spatial direction. Right? This is not the direct distance in space time. Right? Because space time distance is always zero, right? Because light is traveling around the null zero. So it's today what it would have been, right? Right? If somebody could observe both today and measure the distance, right? Which nobody can, right? But if somebody could, then this is the distance that measured. Yes.
When we say interpret this particularly, you're saying today we know the idea about what is the metric.
Yes.
And in that, if the light travels, then how much distance it will come, and we will correct for the time evolution.
Exactly.
By making some observation.
That's right.
And here, can you explain? We started with theta and pi taking to be 0.
Yes.
So if we take some other, say, our position, I took it to say theta equals 0 and pi equals 0. And in the case of the star, I can always choose some other theta pi position.
Yes, but by rotation,
You're saying
you
theta
ca-
phi n can take it to 0.
exactly, right? But you can always rotate your coordinate axis so that is at 0. The theta net equal to 0. Yeah, it's just easier to see the isometry, right? If it is on the z axis. Right? But of course, once you have rotational isometry, there is symmetry about every axis, right? Yes. And if you could, exactly, yeah. If you have a very big meter scale and if you can extend it up to the star, right? That will today, that will measure D. Yeah, so you have to first extend it. You have to make sure that that scale is already in place first, right? Before the star comes. Yeah. As I say, nobody can measure it, but it's a useful quantity in terms of which you can express various formulae. Yes.
Will not T naught because there is sitting.
Yes.
How do we know T1 and R naught for any, let's say, star seen this?
Well, we'll see. I mean, we'll see how you use it, right? You have to reconstruct this T1 and R naught from the various data. Okay, so now suppose that a light emitted at it's slightly later okay, the star is co-moving, so it's sitting in the same place. We are co-moving, we are sitting also at R equal to 0. So we have a similar equation T1 plus delta T1 to T0 plus delta T0 dt over lambda T equal to D. D hasn't changed, right? As long as the objects are co-moving. Is clear? Now we'll take the difference between these two. Okay, so that D goes away. If you take the difference between these two, then basically what you will see is a delta T naught over lambda T naught minus delta T1 over lambda T1 is 0. Is from the difference. Is this clear? Pardon? Yeah, difference between two equations. This one and this one. Right? The right hand side cancels. Where the same D. Right? On the left hand side, only the limits have changed. Right? So the upper limit you get this, and from the lower limit you get this. But this is not saying that they are the same, right? We have used exactly the same information. The light follows null geodesic, right? See, the reason that they are not the same because even though the objects are not moving in space, the metric has changed between T and T plus delta T, right? It's a little later. And that makes a difference. This is my definition. This is a co-moving distance, right? The distance measured in on the spatial slice, right, in today's metric. Anyway, D has dropped out here, right? So you don't worry at this stage. Right? But this is saying that if you have a periodic motion, right, frequency will be like 1 over delta T naught. Right? Imagine that there is an oscillator, right? Frequency will be like 1 over delta T naught. And here, so this is the observed frequency. This is what we are seeing. The actual emitter frequency of emission will be 1 over delta T1. Right? Because this is where the object is vibrating in a star. So nu 0 over nu 1 will be delta t1 over delta t0, because frequency is inversely proportional to the period, and that will be given by lambda t1 over lambda t0. Lambda t0 is by definition 1.
Observers in these two stationary observers.
Yeah, so t is the proper time. I should have said that, because for the stationary observer, right, for the co-moving observer, t is the proper time. You can see from the matrix, right? Because these are fixed for a co-moving observer, right? R theta phi are fixed, so proper time is just t. Okay? ds square is minus dt square. That's an important point. Is that clear? Right? That sort of for the co-moving observers, t is the proper time. Okay?
The analog of statement that we derived towards the static method.
Yeah, so this will be the analog of that statement. But now the statement is because of the time dependent matrix. Now, what you observe in experiment is that this nu 0 observed frequency is less than the actual frequency. How do you know the actual frequency? Because you look at the spectral lines, right? The whole set of spectral lines, we know their intrinsic frequency, right? And we see what we see from here, right? The whole set of spectral lines gets shifted, okay? And it gets shifted towards red, which means that today's observed frequency is less than what it should be. Okay? So if nu 0 is less than nu 1, right, that means that lambda t1 must be less than 1, or lambda t1 must be less than lambda t0. Right? T1 was in the past. Right? So the conclusion is that lambda t must be increasing with time. Is that point clear? Why? That is observation. So what you observe, right? You look at the spectral line that is coming from the faraway object, right? And what we find, we know what the intrinsic frequency of the spectral line should be, because like sodium line, for example, right? They have an intrinsic frequency. When you receive the light here, right, we see that the actual frequency is less. Okay? So this is observation. So nu 0 less than nu 1 is observation. And so this, from this we inferred that lambda of t0 is larger than lambda of t1. But if you look at many lines, right, and if you find that all of them have shifted by some common ratio, right, then okay, unless there is a magic, right, I mean we conclude that that is a sodium line, right? So that's how you do experiments, right? Just one line will not help, but you have to look at many lines. Is this clear? Okay, now last thing I'll say, okay, let me define the redshift first. So redshift of a distant object is defined to be z, which is lambda of t over lambda of 0, t0, which is 1 minus 1. Sorry, other way, lambda of t0 over lambda of t minus 1. Okay. So today lambda of t naught is 1. Right? If you look at a distant object, right, the light that you are receiving from there was at an earlier t. Right? So this ratio is larger than 1. So the difference between that and 1 is what we call a redshift. Other than the Doppler redshift, indeed. So if the Doppler redshift refers to if there are local velocities, local speeds, right? That is not accounted for. Okay, that we can correct for our motion because we know what our speed is because of the microwave background, right? The dipole asymmetry we can use to fix our speed. And for the far away objects, we don't know what the speed is, right? But if you average over several nearby objects, right, then we expect that those after looking the average, right, maybe the Doppler shift will cancel out, right, and we will get the actual redshift. Again, it's a detailed experimental study that you have to do, right, to do all this averaging and so on. So these are redshift other than a Doppler shift. Okay, the Doppler shift because of the local motion.
Explain this one, how observationally we distinguish Doppler motion.
Well, there is no really hard and fast way. You have to do averaging, right? The idea that if you average over many nearby objects, then the Doppler effects will cancel out because those are local speed related to the local inertial frame. And so they have to calculate the average redshift. But this is easier said than done, right? You have to first identify objects in the sky which you believe are nearby, right? Because you are only looking at a line, right? Along the line, you may be, I'm led to think that two objects are nearby even though they're very far away, right? Along the radial line. So you have to find ways to distinguish that. Right? If you can identify a set of nearby objects, right, then you take the average, and then you expect that on the average the Doppler shift effect will go away. Large D. No, it's true for nearby objects also. But Z is just 1. Z is just 0, right? See, if lambda t is equal to lambda, if t is equal to t naught, right, then this redshift is just 1. Sorry, redshift is 0. And now the claim, which I'll try to illustrate maybe later in the next lecture in detail, okay, is that if we can find Z as a function of D, this experiment, right? You have to somehow look at far away objects, right? Estimate what the D is, because as we discussed, measuring D is not easy, right? You have to use standard candles, etc. But suppose you can find Z as a function of D, right? This can tell us, will tell us Z as a function of T, and hence A as a function of T, lambda as a function of T. Okay, lambda and Z are simply related, right? Z is just 1 over lambda of T minus 1. Is this clear? Yeah, so you have to somehow find T as a function of D. Okay? But T as a function of D requires lambda. So it's a complicated set of equations which you have to solve, right? So let me just give an example. I think I have 5 minutes. This is probably 5 minutes fast, right? So let me just describe in brief how it's done. So suppose lambda of T is given by 1. I'm doing an expansion in powers of T minus T naught. Okay. because lambda is 1 today. Okay, so function of t minus t naught 1 minus h naught times t minus t naught. Why have I chosen a minus sign here? Because no, this should be plus. D lambda, it is this plus d lambda dt is positive, that we know. Lambda is increasing, right? So this should be plus. This is some constant. Okay, this is what is known as the Hubble constant. Next term is t minus t naught square. Okay. There is a particular way of parameterizing this. Let me write this: minus half u0 h0 square q0 is a parameter, new parameter. Now, why have I written it this way? I could have just written it some constant times t minus t naught square, right? Okay, Taylor series expansion after all. This half is standard in Taylor series expansion, right? You write 1 over n factorial for the t minus t naught to the n term. I put h naught square because you see this is dimensionless. H naught times t minus t naught is dimensionless, right? Because lambda is dimensionless. Lambda is the ratio of a to a naught, right? So this is dimensionless. So because of this is dimensionless. Okay, just added the introduce the h naught, so to make it dimensionless. Whatever is left, I am calling q naught. This q naught is what is called the deceleration parameter. It tells us, it is telling us how the universe expansion is decelerating, right? Minus sign, right? Because of deceleration. Because it's minus sign, it's called deceleration parameter. No, we haven't observed. So this is because when it was introduced, right, everyone thought it should be negative. And it was a shock when people found that this coefficient is actually positive. We'll discuss what that means, right? Why the positivity of the coefficient was a shock. But that's how it happened, right? So it's called, you still use q naught, right? This parameterization is still called deceleration parameter, but q naught is actually negative. Okay, but anyway, let's take this, and then there are higher order terms. Pardon?
It will eventually take over if it was deceleration.
Yes, if it was deceleration, we'll see how the universe would have evolved eventually, right? But we know that it's not deceleration; it's actually acceleration. Okay, so given this, okay, so this is, we want to calculate these things, right? What we observe is that D is, sorry, Z is AD plus BD square. These are observed. Right? So what one can do is that we just substitute this in this equation and try to solve it. So we have this equation, integral T1 to T naught, let me call it T to T naught, dt prime over lambda T prime is equal to D. Okay. So using this, we substitute for lambda T. Okay, this expansion. and calculate D as Taylor series expansion in T minus T naught. It is clear how to do it, right? You substitute this, right? Do a Taylor series expand. So 1 over lambda t, you have to do a Taylor series expansion in parts of T minus T naught or T prime minus T naught because there's lambda T prime, and then do the integral in the Taylor series expansion. Is this clear? So this is one set of data. The other set of data is that Z is given as AD plus BD square this Z is lambda T, 1 over lambda T minus 1. Okay. Again, this you can Taylor series expand. So you see, we have two sets of relations between D and T. One from here, right? Those relations are given in terms of some unknown coefficients because lambda we don't know, right? Those Taylor series expansion coefficients of lambda we don't know. We are just trying to calculate those, right? Here again, you have a relation between T and D, right? Because this side is given in terms of D, this side is given in terms of T. But here these coefficients we know. And then you have to manipulate these two sets of equations to eventually relate these coefficients that you see here, H0, Q0, etc., to the coefficients A, B, etc. Right? That's the way this calculation is done. Next time, I think we'll go through it in a little more detail and see how this is done. But roughly, this is the idea that if you can find the distance redshift relation, right, as an expansion in power series in D, you can use that to calculate lambda of T as a power series in T minus T naught. Okay, but as I said, that it's a little, it's not straightforward, right? That's one single expression that you can use. Said, okay, this is what gives these coefficients in terms of those. Right? You have to do some analysis, but it's just that you have two sets of relations between T and D. Okay. One set uses only unknown coefficients, the other one uses both known and unknown coefficients. Okay. And you have to compare them to figure out the unknown coefficients in terms of the known coefficients. So this I'll discuss next time. Are there any questions? Yeah, H naught, Q naught, these are the unknown objects, right? So the idea is that if you know A and B, right, this is what you directly observe, right? Well, not very direct, but at least this is what you ultimately conclude from experiment. That what is the relationship between distance and redshift, right? How far they are on the spatial slice versus what the redshift is. Using those coefficients, right, you can determine this H naught, Q naught, etc. Well, homogeneous spaces don't have any singularities. They may have coordinate singularities, okay? But those are very well understood, right? Like sphere, for example, has no single coordinate that covers it. Right? So this r coordinate that you use is singular at r equal to 1. Right? But that's just you can make a coordinate change to figure out what the actual metric is. Yeah. So spatial slices don't have any coordinate singularity. We will see them as a function of time in the early universe, there is a singularity, right? But on the spatial slice, there is no singularity. Directly, yes. No, what we can observe is this apparent luminosity. From there, you have to reconstruct what D is. See, suppose everything was static, right? Then for our objects, we'll have this 1 over r square fall off, right? Because the power that we receive, right? It's the same power getting distributed over 4 pi r square radius, right? So the power that we receive will fall off as 1 over r square. So using the actual observed power versus the apparent power, actual observed power versus what it should have been, right? The intrinsic power, we can figure out how far it was, right? Here it's complicated because the universe is also evolving, right? So you have to correct for that. Okay, but nevertheless, after you correct for that, so I can say that instead of saying Z versus D, right, you can make what you can plot directly is Z versus apparent luminosity, right? Or imagine that you have objects whose intrinsic luminosity you know, right? So the ratio of the observed luminosity versus intrinsic luminosity as a function of Z is what we can observe, right? Because Z you observe because of the redshift, and you see objects with that redshift, how much is the ratio of the apparent luminosity versus intrinsic luminosity, right? That data you can convert to these eventually, H naught, Q naught, etc. Right? Basically, the idea is that in terms of equations, there are all the only unknown coefficients are these, right? So you need some experiment, right, which will determine a few known coefficients, right? And then it's the job of a theorist to convert them to find unknown coefficients in some known coefficients, right? And that there you solve equations, right? Here I have assumed that Z is known, Z as a function of D is known, but if you go even backwards, right, and say, okay, Z is a function of D is not known, but the Z as a function of the ratio of the observed luminosity versus actual luminosity is known, right? That can be used to determine these coefficients. Any other question? Oh, why? Well, solar system is not expanding because there is it's a bound system, right? That we can check. I mean, of course, it doesn't follow from what I have done. But in this expanding universe, if you have a bound system, right, gravitationally bound like the solar system, you can show that that doesn't expand as lambda. Of course, it affects the motion of the solar system. Yeah, that doesn't change because the size of the meter stick is fixed by the molecular and atomic interactions, right? Right? That's what controls the size of the meter stick. So because the molecular and atomic interactions are much stronger than the gravitational force, right? Because of the expansion of the universe, we are not changing. Right? So the meter stick, right? It remains a meter stick even when you expand.
There is an acceleration term sitting there. So at some point.
Yeah, but the point that is very small, right? I mean, that kind of acceleration is not going to affect a meter stick. Yeah, certainly. So you keep going, right? At higher orders, right? I mean, when this expansion breaks down, for example, right? When Z is really far away from 1, right? Then you cannot do this expansion, right? I just gave this as an example of how you do it for small d. Otherwise, you have to solve it numerically, right? If you know Z as a function of D, right? You set up your numerical methods to figure out how lambda will be as a function of, right? Or let me put it this way, that suppose you knew lambda as a function of t, right? Then we could work backwards and find Z as a function of t, right? So then you assume some form of lambda as a function of t, you see if Z as a function of d comes out correctly. If it doesn't come out correctly, you change that, and you see again if Z as a function of d comes out correctly, right? Of course, this is not the way you actually do things, but in principle, this is the way you could do it, right? just try various lambda of t and see which one fits. Right? In practice, you set up a combined equations, right, which gives an algorithm to determine lambda as a function of t. Okay? But the very fact that lambda as a function of t will determine z as a function of d, right, means that z as a function of d will also determine lambda as a function of t. So it's one function unknown, one function known. Small. Small a of t. Which oh yeah, that's so I have now forgotten about a, right? I'll use only a lambda of t as a variable. This one, right? So a naught, as I said, is very, very big, right? We don't know what it is, right? Because that depends on that determines whether it's okay. If the metric was this dx square plus dy square plus dz square, right? Then if you multiply by a0, it has no effect because I could absorb just rescale x, y, z by a0 and write it as dx square plus dy square plus dz square, right? If it has a sphere, then you cannot absorb a0 completely. Right? But what we are saying is that to our current knowledge, we cannot distinguish a sphere from a flat space. So it's as if we have a flat space. Okay? Then a0 has no relevance. Right? Because a0 can just be removed by coordinate change. Right? It's only lambda of t that is a relevant one, right? How much the scale factor was in the past relative to us, right? And how much it will be in the future relative to us. Okay. If on the other hand k was not 0 but plus minus 1, then a0 would be relevant. Right? That will tell us what the spatial curvature is. No, because we don't know if k is 0 or 1 or minus 1, right? Yeah, if k was 1, for example, right, then you know the universe is finite because the spatial slice would be closed, right? There is a sphere. You'll come back to the original point. But because you cannot determine k, right, you don't know if it's finite or infinite. The spatial slice, it can be anything.
This is happening because we cannot determine k
because somehow a0 is so large that it's indistinguishable from being flat. Right? Now you can ask why is a0 so large, right? There is an explanation for that, but for that you will have to wait, maybe not this course, next course. Right? Inflation basically does that job, that why a0 is so large. Right? It also explains why universe is homogeneous and isotropic. Inflation.
The size is larger than the age of the.
No, inflation came for various to solve various puzzles. Right? But one of the consequences of inflation is that this a0 is very large, right? And that the universe should be homogeneous and isotropic. Right? It's basically that in the early universe, right, at some point the universe got very highly stretched. So even if it was a sphere, right, it got so much stretched that today we cannot distinguish it from a plane. Right? So similarly, if the universe to begin with had some inhomogeneities, right, because of the stretching, right, it looks almost homogeneous. Well, it's deflating the fluctuations, but it's inflating the space, right?
This is so inflation also kind of explains why the observable universe may be very smaller than the
Exactly. Yeah. Right? So the actual universe may have this spatial slice may be sphere, right? But we are observing such a small part of that sphere that today we cannot distinguish that from flat space. Yeah, but if you want to determine how lambda changes the function of t, we have to solve Einstein's equation.
Okay, and we have to know the meaning of the whole.
Yes.
universe.
Yes. That will do eventually. Right? Maybe next class itself will start.
General form we got this
Based on symmetry, exactly. Yes. Oh, average. I don't remember the exact number, but it's like hundreds of megaparsecs, right? And a parsec is like 3 light years. So megaparsec is 10 to the 6, right? Parsec, and then hundreds of those is what the distance over which you average. So it's a huge number, but the universe size is much bigger, right? So it makes sense to average.
I don't know whether it's about to ask you this or not. I wanted to ask you about that assignment question, which an accelerated observerism. So, is there any other way of doing that question other than going to a local inertial frame, finding its coordinate transformation, and then inverting it?
Yeah, you try to do it by going to a local inertial frame, right? I mean, that's the foolproof way, right? I mean, you have to understand what this feeling a constant acceleration means, right, in terms of equations, right? But maybe once you understand this, then you can try to simplify things, right? But I mean, you do it by, this is the basic principle from which you start, right?
So basically, find out the coordinate transformation.
Exactly, yeah.
To the local.
Yeah.
I thought there is some other less tedious way.
Yeah, but okay, it's you have to live with it.
Asif, Mike.
Oh, and somebody left